Alright, so I'm going to talk a bit about bonding theory in this video. So in a previous video I said that we can build up the electron configuration of an atom. So let's say it's carbon. So that's C. That's C, carbon. And I said that this has in its valence shell, it has 4 electrons with 2 in its inner shell, and so that would be 1s, 2, 2s, 2, and then we have 2p2. So that's the 6 electrons. So I'm not showing the 2 inner electrons here. So these are our various orbitals. However, when we're bonding, these atomic orbitals then become hybridized orbitals. And so in this case, we will, just ignoring the inner electrons for a minute, we will promote one of these S's to a P. So we have 2p3. So that's our 4 valence electron shells. And then what can happen is these electrons here can become hybridized, so that instead of 1 2s orbital and 3 2p orbitals, we now have 4 orbitals that are defined as sp. And since we have 4 of them and they're made out of 3 p's and 1 s, we write it as s and then p3. And so that's what this is showing up here, is we're taking our s orbital here and then our 3 p orbitals here and turning it into this sp3 hybrid orbital, which is the tetrahedral shape that you see in the carbon. For instance, when we had carbon with 4 hydrogens on it, like this, and that's why we have this tetrahedral shape in our hydrogen, because this carbon has these 4 hybrid orbitals like this, which are then bonding with the s orbital on these hydrogens here. And so I have over here just another way of showing it, where we have the s orbital and the 3 p orbitals hybridizing to become these sp3 hybridized orbitals, which then, as you can see here, forms this tetrahedral shape. And with carbon particularly, we can have other hybrid forms. So we could have something like our carbon with so let's say we have double bond to oxygen and then hydrogen and hydrogen. And so this only has 3 hybrid orbitals, so it's called sp2. So it's s and then it's 1 part s, 2 parts p, and this other bond here in the double bond remains as a just a regular p orbital. And so if we try to shift the perspective on this, we have our sp2 hybrid orbital going to the oxygen, and we have one of the h's going into the page, one coming out of the page. So we're sort of looking at this flat on, and you can see in that case, instead of this tetrahedral shape, we have more of a triangular shape on here. So this will make what's called a trigonal shape, where there is 120 degrees of separation between these bonds, where on something like this it's less. I don't remember offhand, but it's less degrees between these, since there are 4 of them and they're in this tetrahedral shape. It's something around like, it's not 90 degrees. I think it's something around 100 degrees maybe. So these 120, 240, 360 has up to 360, so you have the whole degrees, you have the whole circle around that makes this a triangle. So we can look at this as a triangle, and this has the sp2 going to that hydrogen, an sp2 going to this hydrogen, and an sp2 going to this oxygen. And so the oxygen and this carbon now are still left with p orbitals like this, and these p orbitals have sort of an interaction like this, going back and forth between them, like on both the upper part and the lower part. And so that's what makes up our double bond. And so when we have 4 single bonds in our carbon, that's sp3 hybridized. When we have 3 bonds plus one of these double bonds, that makes it an sp2 hybridized. And we can also have sp hybridized if we have, for instance, carbon dioxide is sp, and so in this case we would have a carbon that has the sp bond to oxygen, sp bond to oxygen, and then sort of coming out of the screen and going into the screen we have p bonds, or p orbitals, and then coming off the top and the bottom we have p orbitals. And so one of these on the oxygen will have the p orbital on the top and bottom where these are interacting, and then this will also have the p orbital going into the screen and out of the screen with those interacting, making the 2 double bonds with the carbon, and that would be sp hybridized, where this is sp2 and this is sp3. And so you can actually get what's called these conjugated double bonds. So conjugated double bonds. So if you have a repeating pattern where this is a double bond, then this is a single bond, then this is a double bond, and you have your p orbitals that are pointing up like this, similar to how I showed right here and right here, where we have our p orbitals still free, and those have interactions going on between them. But you can see we also then can have interactions going on even at this single bond, and so we have somewhat of a double bond character even on the single bond, which right here it says it's a barrier to rotation. You do not have any free rotation around the single bond as you would usually find in a normal single bond. For instance, if you have C, then just arbitrary R's coming off of them, you can rotate around this single bond and you can end up with this. And this is in sort of an equilibrium. It's sort of always rotating because there's energy, so there's always this rotation going on. But when you have these double bonds, you cannot have rotation. If you have this, then these two R groups are always going to be in this opposite or trans direction, and same as if you have it like this, then they will always be in this same cis direction. And so this is showing that because we have this double bond character where these p orbitals are sort of shared across the entire molecule, then you are losing that. You have a barrier rotation. You're losing the ability to rotate. And we can think about this in terms of what's called molecular orbital theory. So molecular orbital, this is MO theory. And so right here we have our four p orbitals, and we can think about them in this way. So these different colors are the phase. It's a quantum mechanical property of orbitals. And so when they're in phase, you can think about, if you know about like how waves work, when you have a wave like this, if you then combine it with something in phase, then you get something that has constructive interference, where it has a much larger amplitude here, whereas if you have something like this where they're out of phase, then you will end up with zero amplitude. And so when these are in phase, this is bonding. That's why it's called bonding here. And then we have these two in phase and then these two in phase, which is also bonding. And that's why we show it with the double bonds here and not in the middle, because there's sort of a partial loss of phase between the two. So it's not a full sort of double bond here. It has double bond character enough that it is a barrier rotation. And so we end up with the two bonds like that. And then up here, we start getting into the anti-bonding, where everything starts getting out of phase. But you see, we have our four p orbitals are enough to fill up these. So there's two in here and two in here. And so we end up with all this bonding character. We're not breaking any of the bonds on here. And this can also be thought about if you have taken much quantum mechanics. You've probably done the so-called particle in a box. So here's our box where there's infinite potential on either side. So the electron can't escape the box. This would be sort of like having this as our wave function inside the box. Then the next one over would be sort of like having that as our wave function in the box. And then this, as you can see, we start out up here, and then it goes down like that, and we see that that this is creating sort of an issue here, where our amplitude is too high at the end, because this needs to fall off outside here, because we have an infinite potential. And so this becomes the anti-bonding sort of molecular orbital. And so over here, down here, we have our bonding, which is, you can think of this molecule as the box. The electrons aren't escaping off either end of this molecule, so that can act as our potential on the box. And so that is, I think that's all I had for bonding theory. And so yeah, just to review, we can have our sp3 or sp2 and our sp hybridized bonds, and whenever you leave one of the p orbitals off of the hybridization, then that can form this double bond. And you can leave two p orbitals off, so that you're forming these two double bonds. And because of these free p orbitals, if you have this conjugation, then you can have this sort of double bond character, these p orbitals being shared over the entire molecule like this. And these are called dienes when it has these two double bonds like this, because double bond is what's called it's an ene when you're naming molecules. So, for instance, we can have our CH3, HC3, and this is ethane. But if we have H2C double bond to this, then this is called ethene. And so butane, it's a 4-carbon chain like butane, so but, then di2, which means 2, because we have 2 double bonds, which is ene, so ene. And so there's a logic to the way that these are named, and the 1,3 just tells you where those double bonds are. So this is the first carbon, this is the third carbon, so 1,3 butadiene. Alright, then this is our molecular orbital theory, as I said, for the butadiene, and we have the in phase down here and the mostly in phase here, and that's how you end up with these conjugated double bonds. Alright, so I hope that was helpful insofar as bonding theory goes. Actually, there was one other thing that I had wanted to talk about here, and that had to do with these hybrid bonds and the way that they work in what's called orbital steering. And so we can think of maybe a C going to R, and this is an oxygen which has the sp double bond here from the carbon, and we can have other sorts of we can have free hybridized orbitals that are coming off of this. So that's not very good. So we can have our hybridized orbital coming off of this with 2 electrons, and this has 2 other pairs, but we won't worry about the hybridization of those. So this has, it's negatively charged. This has this this hybrid orbital, and so we can think of H plus as having this s orbital that has nothing in it. It's an empty orbital, and this has the hybrid orbital, and these these will fill up this empty s orbital so that we can create our C. I'll make sure to put that on there. So we have our hybrid orbital overlapping with the s orbital, so that the electrons are now shared between the oxygen and the hydrogen. And orbital steering is the idea that if you align this well with what you're trying to bond to, so this might work better if we're thinking about, say, a carbon, and then we have an oxygen here which has the sp hybrid orbital, and then our carbon also has a sp hybrid orbital. And if these align well, then you will actually get bonding faster than if you had this, and then say our oxygen was like this, where these orbitals don't overlap as well. This is our sp hybrid orbital. And so the bonding works better, it works faster if we align these hybrid orbitals better. And I'll get more into detail on this when we start talking about enzyme kinetics, because this is very important for enzyme kinetics. When a molecule enters an enzyme, we have a substrate here, and we have our enzyme, and what happens when the substrate enters the enzyme is the enzyme changes its conformation in such a way that the active site, the enzyme, steers orbitals in such a way that it can catalyze reactions with these substrates much more quickly. And so that's this idea of orbital steering, which comes out of this idea of hybridization and molecular orbital theory. So like I said, once we get more into the biochemistry, that will become more important, and I'll see if I can explain it perhaps in more detail, and maybe even quantize or quantify, how much this orbital steering actually makes a difference in how reactions occur. And so, anyway, I will see you in the next video.